Welcome to today's webinar. It's a step-by-step introduction to 2D reinforcement analysis with LimitState GEO, which is our geotechnical stability analysis tool. I'm Tom Pritchard. I'm the principal engineer here at LimitState, and I'm your host for today. Our main speaker is Professor Colin Smith, who is the LimitState GEO product manager and also the developer of the DLO analysis method, which underpins the software. Today's webinar is going to last about half an hour, and there's time for a few questions at the end of it. So please do feel free to post them at any time, and we'll try to get around to them at the end. As always, if we don't manage to get around to them, then we'll make sure to follow up by email with each and every one of you after the webinar is finished. The recording of the webinar will be made available in the days following through our YouTube channel, and be sure to keep an eye out for that. We will send out an email just to remind you about it. I'll return to that at the end of the webinar while I wrap up, but for now I have the pleasure of passing you over to our speaker for today, who is Professor Colin Smith.
Okay, thank you, Tom. So we'll just crack on straight away. There we go. Yeah, so by way of introduction to the software, LimitState GEO is a fully general ultimate limit state analysis program designed to identify the critical collapse mechanism for any problem type in the form of a slipline mechanism, as you can see in these examples. And in terms of what we're going to talk about today specifically, we'll be looking at modeling a reinforced slope using two-dimensional geotextile reinforcement and be demonstrating this process step by step. As it's a short presentation, the main aim is just to give you a flavor of what the software can do, how to set up a problem, and there won't be time to get into the details of all the software functionality. However, there'll be time at the end for questions. So let's look at an example. So we're going to model a reinforced slope, 8-meter high slope in a cohesive frictional soil, reinforced with geotextile layers, as you can see on the right of the model. There's a variable surface surcharge of 10 kPa. It's founded on a stratum of soil, similar strength, slightly stronger, and we will have the model geometry available as a DXF file. And we obviously want to analyze this, so we capture both internal and external failure, all the aspects of a reinforced soil problem, and LimitState GEO does this inherently. We don't need any extra specifications to get it to do that. Let's look at the properties we want. So as I said, the model is available as a DXF file. The soil we're going to model cohesive frictional, C' of 2.5, phi' of 35 for the main slope stratum, and the base stratum a little bit stronger, C' of 5, phi' of 38. And the geotextile properties, rupture strength of 14.4 kilonewtons per meter, adhesion factors of 0.8. But we'll come back to those a little bit later. For the moment, we're just going to build the core model now from the DXF file and add in the soil properties and the boundary conditions. So we'll now build that model. So what I'm going to do is bring in the LimitState GEO window. I'll explain various buttons and functionality on this as we go along. So first thing I want to do is import a geometry, and I'm going to got a particular file here, reinforced slope DXF. I have some options to adjust the geometry. I'm just going to accept the defaults, and we get a geometry like this, which is similar to what you saw in the image. It has some construction lines. If I use the right-click option on the main screen, I get a pop-up dialog, and I can clear all the construction lines. We don't need those at the moment. So you can see that the geotextiles here are modeled as boundaries. That's where we're going to put those. And in the software, you can't have free boundaries with free ends. So we have to link them up with dummy boundaries at the end here. So these dummy boundaries don't actually do anything. So we're going to define some soil properties. So we use tools up here, create new material. We want a more cooler material, give it a name. So I'm going to call this the slope stratum. We can give it a color, something grayish in that case. It's a cohesive frictional soil. We'll say it's always drained. So the C' property was 2.5. The friction angle was 35, and the unit weights were 18 and 20. So click OK on that, and you'll see up here on the left we have a material that's appeared in what we call the Materials Explorer. So these are all the materials available to you, user-defined ones and some built-in ones if you want to do some quick sort of what-if type calculations. And then I can populate the domain with that. I can use drag and drop, so I can take that material, drag it across, put it there, drag it into these zones and so on. Or alternatively, I can hold the control key down and select. The control key does not seem to be working. It is working. Select these blocks all at once, and then on the right-hand side we have what's called a property editor, which tells you the properties of what you've selected. At the moment it says material, we have no materials assigned. I can click this little change button here and actually pick the material I want, the slope stratum, and they all become the same. So that's an alternative way of assigning properties. I just need to create the base stratum, so it's very simply the same thing, same process. Like a color, and always drained, and this time we had 5 and 38 and 19 and 21 for the unit weights. Again, that appears up here in our Materials Explorer. I can drag and drop that into there. So we've now added our materials. We can put in our surface surcharge. So anything I click on in the software, the properties appear in this property editor on the right. So I've clicked on a boundary and I can specify loads on a boundary. So here I get a choice of defining permanent, variable, or accidental in line with Eurocode definitions. We're going to say this is a variable load. It's a normal load of 10. And I can specify whether it's favorable, unfavorable, or neutral. That's really to do with Eurocode factoring, which we're not going to have time to go into today, but just for consistency, I will make that unfavorable. So now we have our load up there. Now I need to set some boundary conditions. So again, here I want a fixed boundary. So again, the properties are here and the support type. I have a choice to make that one fixed. And again, I can, if I hold the control key down, just do 2 there, I can make those 2 fixed at the same time, and then 1 more. That's just got our boundary conditions. And I'm going to set this for, we can solve the problem in 2 ways. We can ask the software how much bigger does a load have to be to cause collapse, or how much weaker does a soil have to be to cause collapse, and generally that's the one we want for slope stability type problems. So I'm going to switch to that mode, and then I'm going to solve it. I haven't put any reinforcement in, but it's useful to see what happens in that particular instance. So it goes through a few iterations, trying a few different failure modes until it homes in on the critical failure mode. And it's what it's saying. If I click on this solution down here, we have an adequacy factor and material strength. If I click on that, what it's telling me is it basically needs to factor all the strengths by dividing by that number, i.e. making them bigger, to get the system at the point of collapse. So clearly that slope is very steep. It's not stable. It's going to collapse, and the soil needs to be a lot stronger to cope with that, or we need to put some geotextile, some reinforcement in, which is what we're going to do. So I click this button up here. This is unlock. That just takes us back to edit mode. And as you saw, the failure mechanism, I'll just run it again, was in the form of a slipline mechanism, effectively made up of lots of different wedges. So if you like, it's like a Coulomb wedge analysis, but we can analyze tens, hundreds, thousands of wedges and get very accurate slipline solutions. And the software will always find the critical collapse mechanism. So all I've got to do is specify the reinforcement, but let's just unpick those reinforcement properties in a little bit more detail before we do that. So modeling reinforcement. Two main things we're interested in is essentially the pull-out force. So for a drained soil, which is what we're modeling here, the conventional assumption is that the shear stress at failure on the reinforcement is a factor alpha, our interface friction factor, multiplied by the normal stress multiplied by tan phi dashed. And so the total pull-out force, if we've got a length L, is 2 alpha sigma n tan phi dashed, multiplied by L, which I've missed off my slide. And it's 2 because we're using the shear stress on the top and the bottom. And typically in hand calculations, conventional calculations, the average normal stress on the reinforcement is typically taken as the weight of overburden at that depth per unit area. And that's what the software does automatically for you. It can also model tensile failure within the reinforcement. So if the tensile force in the reinforcement exceeds the tensile strength, then the software will model a ductile failure and the reinforcement will effectively stretch within the failure mechanism. This diagram shows a failure mechanism of the soil and how those interactions happen. So we take on the left, you can see in this area, the reinforcement is being pulled out of the soil body on the left that's not deforming. At the next level down, effectively the reinforcement is failing itself, essentially stretching with the mechanism. And on the base here, we have the reinforcement is effectively anchored into the stable soil on the left, and the soil is pushing past it. So you can see it's pushing past the end there. So we can capture all those modes, and in addition, sliding on one or other face of the geotextile. That's all modeled inherently. So how do we specify those properties in the software? The recommended approach is to use what we call an engineering element in the software, and that can be used to represent geotextiles as well as soil nails and sheet pile walls, for example, a specified tensile rupture strength R. And then we combine that with interface materials above and below the element, which allow us to use those alpha factors. We use that using what's called a derived material. I'll show you how that's done in a moment. And we assign them to the boundary where that reinforcement is. So just to remind you, we want a geotextile property. It's rupture strength of 14.4, adhesion factor of 0.8. So we'll jump back to the model and we create those properties. So first of all, tools, create new material again. This time we select from this drop-down box an engineered element. And I'm just going to give it a name. We're going to call it reinforcement. Red color. The application, we choose geotextile here. So it automatically specifies certain properties, and the only property that we actually need to worry about is a rupture strength. So I'm going to put in 14.4 here, and that's created that material, and that's up here. So I can, for example, drag and drop that onto this boundary, and that's put a reinforcement element there. I then want to create the interface material. So I'm going to create another material, this time what's called a derived material. So that's a soil reinforcement interface material, blue. Now, this derived material effectively derives its material properties relative to an already defined material. So we're going to pick the slope strata material. And what we're going to say is that its strength has to be 0.8 times slope stratum strength. So it's got an angle of friction of 35 degrees, for example, and point to that is 28 degrees. So we'll be modeling the interface at 28 degrees, and similarly with the cohesion, the C-dashed value, cohesion intercept factored. So that's defined. And again, I can drop that on there, and that I will add it. So I get both those materials there, and if I zoom in on that, you can basically see the reinforcement of the interface above and below. If I click on that, in the property editors, you can see I've got material top, center, and bottom, and the engineered element, my reinforcement, and my interface material is above and below. So that's modeling the properties. And with that derived material, if I ever change the properties of the slope stratum, its properties will, of course, mirror that, but scaled by 0.8. If I click this button here, I'll zoom back out to where I am. So I can then also assign properties to the other ones. I'm going to do this in a block. So if I start here, if I use on the left, I use this rectangular select. I drag a triangle, a rectangle that just goes over the boundaries of interest. I select those, both the boundaries and the solids of interest, but in the property editor, I can select a subset. So I'm going to select the subset that are just the boundaries, and then I can change their properties. And then I can put on the reinforcement and the interface, click OK, and I've assigned all of those. You can see they're all there as before. For aesthetics, we could also avoid showing these boundaries here. I can just assign the slope stratum to that, which makes it vanish. It won't change the analysis in any way, but I can do that. And again, if I want to select those, I could triangle select from the top left, just select that boundary on its own. And again, if I select the boundaries of that, I can change those to the slope stratum. And I have my model. Okay, so we can now solve that, see if that makes a difference. So I click solve again. See if we get a more stable slope. Again, it's iterate through a few mechanisms in order to find the factor on strength. And it's come up with factor on strength of 1.177. So that means we have to divide the soil properties by 1.117 to get failure. So that means we are actually stable. We have a margin of safety of 17% on strength in this particular problem. If I animate this, you can see the mechanism of failure through that reinforcement. But what is actually happening is the reinforcement itself is yielding. And we can see that these graphs, these little red graphs on each reinforcement, tell us the properties that are actually in the reinforcement. So the axial force you can see here is actually reaching that yield value. So we're actually failing the reinforcement. The slope is still stable, but we could make the reinforcement stronger. I could change its strength here to 30 and run the problem again. And we get a very simple failure mechanism. Not very interesting, but essentially we have an improved factor on strength. So we've got a bigger margin of safety, almost 30%, and our failure mechanism is a bit boring, but it is effectively a very simple slope failure that's happening up there in the corner. Now that mechanism is somewhat limited by the density of nodes, which I'll come back to later on. But essentially, the reinforcement is now strong enough to prevent failure through that mechanism. I'm going to click this undo button, which will just reverse the setting for the reinforcement strength. So with that one, I still had a system which was effectively was slightly over-designed. I should say that we haven't applied any safety factors here. I haven't got time to discuss that in detail, but very quickly, we have what's called a scenario manager, which allow us to apply partial factors. And I can, for example, pick the Eurocode Design Approach 1 Combination 2 factor set, which essentially put factors on the material properties. Software will automatically apply that. So if I solve this, we'll get a somewhat similar failure mechanism, but it will we'll get a margin of safety that is less than the value we had before. And in the software, those factors are applied to the soil properties, but not to the strength of the geotextile itself. So there's the similar failure mechanism that we had before, but our margin of safety has dropped to 0.93, which means that the system isn't strong enough. It will fall down, and actually we have to make the soil stronger for it to stand up. So we'll revert back to a unit set of partial factors. And then just to wrap up, we'll say, well, with this original design, we had about a 17% margin of safety, so we could perhaps change the lengths of the reinforcement. I can move those around manually or change their coordinates. If I click on a reinforcement, I need to go back to point select here. I can see the X coordinates here, and I could adjust those by typing in values, or I can just drag one end of it, make one longer and stronger, longer or less long. If I click the ortho button down here, any dragging that I do will only be horizontal or vertical. And then perhaps I could have a go at dragging some of these bits of reinforcement, slightly different configuration. Let's see if we can. And then I could solve that. And if I wanted, I could reconfigure the reinforcement layout. And maybe I would get I'm going to get a lower factor of safety, but it may still be above 1. We'll see. So actually changing that reinforcement hasn't changed the margin of safety by much. So actually we've used less reinforcement and got the same margin of safety. So some of that reinforcement was redundant. But anyway, I think you get the impression, we can play around with a model quite happily, do what if type questions. Okay, so I think that's pretty much all I want to show you in terms of the software. We'll just wrap up by giving you a quick explanation of how this software works. So as you see, we get slipline mechanisms, and this is generated by a numerical method called discontinuity layout optimization. That was published back in 2007, and essentially it's quite a simple problem to describe. We start with a domain. Here it's a rectangular domain for load onto the surface, supports to the left and the base. Instead of discretizing it to elements, we populate it with nodes. Here I'm just using 12 nodes. Typically we use 500, 1,000, 2,000 nodes. And then we connect every node to every other node, and then use optimization to select out of that set of lines the critical ones that form the critical collapse mechanism. And in this case, I think there are about 60 odd lines. There are 6 that form the actual critical collapse mechanism for this very simple problem. And you get that in a slipline form. And so the software will rigorously get to the most optimal mechanism that it can find given the initial layout of nodes. The more nodes you put in, obviously you're going to have a more accurate problem. The other good thing about this method is that it inherently deals with singularities. So this is a Prandtl punch problem or a bearing capacity on clay problem. it can get within 1% of the exact solution in about a second. And at the corners of the foundation, we have singularities where slip lines meet at a point. This could be quite challenging for finer elements to deal with, but this numerical method deals with that inherently. No additional programming is required. Okay, so I think that pretty well wraps up. So just to summarize, hopefully you've seen that we can model reinforcement. We use the same mechanics as conventional methods, such as wedge analysis, but we can effectively model thousands of wedges. We don't need to separately consider internal, external failure, pull-out lengths, or reinforcement rupture. That's all inherently handled by the model, and the method automatically searches all possible failure modes every time you solve. Hopefully you see the workflow is pretty straightforward from geometry importing. I didn't actually show the reporting, but we can generate reports for any problem that you've solved. We can deal easily with a partial factor, solve a problem with one mouse click. And you can see we can play around with the geometry and the properties quite easily and do what-if type questions, which gives you a chance to get a better feel for the problem. And it obviously doesn't just solve reinforcement problems, as you saw right at the beginning. It can solve a wide range of ultimate limit state problems. Okay, so we wrap up there, and hopefully we have a little bit of time for questions. Okay, so we've got a question about how to model water. So the easiest way to model water is to put in a water table. So we have a tool here on the left that allows you to draw in a water table. So I can put one in there, finish, and that puts in a water table here. So if your slope, for example, got flooded, and then we can solve that problem again, and we should end up with a lower margin of safety, because obviously, well, in this particular case, yeah, let's just, yes, as long as the mechanism involves the soil that is flooded, then we should get a lower number. Right to that solution. Yeah, so it's gone down a little bit, but not a huge amount. But we've only flooded the sort of lowest levels. Should be getting there. Yeah, 1.15. So it's gone down slightly. But the reinforcement is obviously playing its part. So if I undo that. And another question, how do you stop local failure that we saw in some of those models? So where we got a failure of just when I made the reinforcement stronger, we got that failure just at the very top. What we normally recommend is that clearly in the field, if you had a local failure like that, it might be suppressed because of vegetation, or the soil on the surface is slightly stronger, is drier, got a bit of unsaturated strength, or you might put in some kind of mesh or netting. What we would recommend in the software is that we model a thin layer of soil on the surface with a slightly higher strength. I've got something changed in the model here. We didn't get that local failure. But anyway, we generally recommend putting a thin layer of soil on the surface with a higher C' value that is sufficient to suppress that local failure. And that's quite good at representing those scenarios I described a bit earlier, where you've got some local strengthening of the face. Okay, I think that pretty well takes us out of time. So I'm just going to hand back to Tom to wrap up. So thank you for listening. I hope you found that useful.
Thank you, Colin, and thanks to everybody who managed to attend today. As mentioned at the beginning of the session, we'll be uploading a recording of this webinar to our YouTube channel, which is LimitState Software, in the next couple of days. And there you'll find a wide range of informative videos on the various applications of LimitState Geo and our other software products. So do take a look, like and subscribe if you want to be kept up to date on that. LimitState Geo is available to download from our website, and you can use it in trial mode for free for 30 days. If you're not familiar with the software already, it's a good opportunity to see what it can do for you. So do visit limitState.com/geo and find out about the software for yourself. And lastly, we do run webinars like this one throughout the year, so do look out for the notifications of the future events, which we'll send out via email, as well as posting on our website and the LimitState LinkedIn page. So finally, thanks once again, everybody. We do hope to see you again at one of our future sessions. Goodbye.